absolute value is what we're going to talk about today. This idea of absolute value. There's the formal definition of absolute value. So absolute value of A is A if A is greater than or equal to 0, and it's negative A if A is less than 0. Another way of thinking about absolute value is, if you imagine the number line is simply distance to 0. So that way we're not worried about plus or minus, it's just how far away it is. That's another way of thinking about it. So we're saying it's magnitude only, so where direction is not considered. That'll make it probably a bit more sense once we start looking at some applications of calculus and derivatives and what have you. So the plus or minus we don't care about, it's just the size of the number itself. Some very easy basic ones to start off with. So absolute value of minus 5 then is just simply 5. I don't care about the minus, how big is the number. It's 5 units. Absolute value signs are just grouping symbols, so we treat them the same. So we do whatever's inside first. 6 minus 8 minus 2 gives me negative 4, so the absolute value, negative 4 is 4. So once again, if we've got something outside the absolute value, we do what's inside the grouping symbols first. So 6 3 is 18, minus 20 is negative 2. So we have 7 minus the absolute value of negative 2. So 7 minus 2, which is 5. And again, just like grouping symbols, I don't put the multiplication sign in this situation. It's just saying 3 times the absolute value of negative 6. So 3 6s are 18. So absolute value equations and inequations. It's very tempting to just look at this and say, oh, x is plus or minus 7. Okay? Which of course is the answer. But the way we should be thinking about it, let's get a more involved one. Say I had absolute value of 2x minus 3 is equal to 7. The way I think about this, I don't say 2x minus 3 is plus or minus 7. Right? It all comes back down to what the definition is. The definition is the absolute value of A is either A or negative A. That's the two things it can be. Now it might seem trivial, might seem pedantic, but we're not saying 2x minus 3 is 7 or 2x minus 3 is negative 7. I'm saying 2x minus 3 is 7 or the negative of 2x minus 3 is 7. So it's the absolute value that's changing, not the other side. Now, it might not seem much with an equation, but it becomes very important when we look at an inequation. So I get x equals 5 or x equals negative 2, so putting that all together in one nice answer. So same idea here. If I've got absolute value of 2x plus 6 is 3x minus 1, then either 2x plus 6 is 3x minus 1, or the negative of 2x plus 6 is 3x minus 1. And then I solve each of those independently. 7 on the left hand side and negative 1 on the right hand side. However, as with all equations, and we've been telling you from the day dot, and you've ignored us from the day dot, you should always check your answer. Because this is another one of those situations where we have created a solution that is not a solution. If you look at x equals negative 1 closely and go back to the original equation. Now the original equation, absolute value of 2x plus 6. Well, if x is negative 1, that's saying the absolute value of negative 4, which would be 4. The right-hand side of the equation would be saying 3 times negative 1 minus 1, which is negative 4. Well, it's not true to say the absolute value of something is negative 4. So the x equals negative 1 is not a possible solution. So when we have broken up the equation into two parts, we have created two new equations. Now, the solutions of my original equation will be in there, but I've created new ones. That's why we check. So x equals 7 is the only answer to that particular one. Now, if you think about it, the only time this situation is going to arise is when you have absolute value equals and then some algebra on the right hand side. Because it's the substitution of the negative number that caused the problem in this case. If you've got absolute value equals a constant, well, it shouldn't arise. But we should still be checking. So why is it different with an inequation? This is where it gets really important. Because it's either x plus 5 is less than 2 or the negative of x plus 5 is less than 2. treating it this way, I don't have to worry about the inequality sign. It'll just fall out naturally. I get x is less than negative 3, and eventually you'll notice I end up dividing or multiplying by negative 1, which means I've changed the sign. So if I change the sign, we change the sign, and I get x is greater than negative 7. Had I done it the other way and said x plus 5 is less than negative 2, I would have come up with an incorrect answer. Okay. So it all goes back to the definition of absolute value. The absolute value of A is either A or negative A. So wherever the absolute value sign, that's what we're changing to, positive or negative. And let's plot that on the number line. There we go. I've got x is less than negative 3. Oh, hang on a sec. X is greater than negative 7. No. Combine those answers. My final answer is x is in between negative 7 and negative 3. Okay. 3x plus 2 greater than or equal to 1. Once again, either the positive of 3x plus 2 or the negative of 3x plus 2. I get x is greater than or equal to minus a third. X is less than or equal to negative 1. And in this case, you'll notice once again we get this situation of either we're in between two numbers or on the outside. And we should find that for these basic linear ones anyway. We should find that all the time. Okay. What effect does it have with graphs? What does absolute value do? Now, there's a whole range of these. We're just going to look at a couple of them. In extension 2, we have all sorts of fun absolute valuing the right-hand side, the left-hand side, both sides, and it changes the graph. But the key ones, I suppose, is y equals the absolute value of function x. What does that do to our function? Well, basically, whatever is below the x-axis reflects above. Because if we're saying y is the absolute value of function x, it would be impossible to get a negative number for the y value. So whatever's below is reflected above. Whereas function absolute value of x now, what happens is whatever's on the left-hand side disappears, because you can never substitute in a negative number into the function. You're substituting in the absolute value into the function, so you're always substituting in positive numbers. So what ends up happening is left-hand side disappears, and then whatever's on the right-hand side is reflected over. So it becomes symmetric. Reason being, sub in negative 2, you're actually subbing in the absolute value of negative 2, so you should get the same answer as 2, same y value. And every number will be the same. The negative will give you the same as the positive. So y equals absolute value of x. Well, we should know what that basically looks like, but there we go. Ooh, there it is. So it's our V shape. Now for absolute value of x, that is a right angle at the base there, because we know y equals x is at 45 degrees. It's usually handy to plot a couple of points to give it some sense of scale for the diagram. So 1, 1 and negative 1, 1. But how do we transform it then? So if I have y equals the absolute value of x plus 2, I can think of it this way. I go, hang on, the basic curve is y equals the absolute value of x. What have I done to it? Remember, absolute value is a grouping symbol. So the 2 is grouped with the x. So we are shifting it horizontally 2 units. And so that'd be our graph. Y equals the absolute value of x plus 2. Of course, another way I could have thought about that one is I could have said the basic curve is actually the line y equals x plus 2. But now I'm going to reflect what is below above, because I'm saying absolute value of function x. So, boom, I get the same shape. Thank goodness. I'd be in trouble if I got a different one. Absolute value of x plus 2. So now I can say, oh well, I've got my basic curve, y equals absolute value of x, but then I'm adding 2. This time it's grouped with the y. So we're shifting it up 2 units. And there's y equals absolute value of x plus 2. Of course, another way I can think about it, I can say, hey, I've got the basic curve y equals x plus 2, but this time it's function absolute value of x. It's only the x I'm doing the absolute value. So whatever's on the left disappears, and whatever's on the right reflects over. And again, I get the same picture. They don't have to be straight lines, so linear functions. Y equals the absolute value of x squared minus 2. Well, there's my parabola y equals x squared minus 2. So I'm simply going to say, well, whatever's below reflects above. So there's y equals the absolute value of x squared minus 2. If I wanted to, I'm not suggesting that you would do this, but, you know, if you already had the graphs drawn, you could use your graph to solve the inequality. We're saying absolute value of x plus 5, so absolute value of x shifted left 5 units. We want to know when is that graph below y equals 2. So when is the blue graph below the red graph? Now I've still got to find the points of intersection, so I've still got to solve it like it's an equation anyway. But I can read off my graph and see, oh, it's just the x values in between minus 7 and minus 3. As I say, I don't think it's a real efficient way of solving that, but had I in a previous part of the question drawn those graphs, and I've got the graphs there to use, and it's accurate, well, in that case, okay, maybe I'll use the graph to solve it. Oh, 3 dimensions, 3D. So we're in space. And then we'll do 3E.